Welcome to Structural Engineering Online. In this video lecture, we will learn how to calculate area moment of inertia of a T section. Please subscribe to our channel if you have not yet subscribed. Subscription is completely free. In this question, we will learn how to calculate area moment of inertia, which is also known as second moment of area, of a T section about its centroidal axis. So in this question, first of all, we have to locate where the centroid of this T section, and after that we will calculate the moment of inertia about its x-axis and y-axis. So first of all, let us assume its position, suppose somewhere here, because this will not be in the middle, and let us say that this distance. And to find this position, we first define the reference line. So with reference to a baseline, you can say, okay, suppose this is our baseline, and the vertical we can take somewhere here. This is our vertical reference line. Suppose this is point A, this is B, and this is point C. So AB is our reference line, which is horizontal reference line, and AC is vertical reference line. So distances in the directions horizontal will be measured along this AC. Now the formula to locate this centroid, which is your, suppose this is y bar, the position of centroid, it is somewhere here, this is point O, and your y-axis somewhere like this. So this is x-axis and this is y-axis of the section. So we have to first locate where is the centroid of this section. Let us say that this is x bar, okay, and this is y bar. So first we have to locate the centroid of this section, and to find the centroid of any section which is composed of different shape. For rectangle, we already know that it will be at the center, but for similarly for triangle, you already know that the position is 1/3 from one side and 2/3 of the base from the other side. But here we have a built-up section which is consisting of two rectangles. So first thing is that we should divide it into those standard shapes. So we can say that we have here one rectangle and we have another rectangle here. So there are two rectangles. You can say one rectangle which is horizontal, one rectangle which is vertical. So now we have to calculate by using this formula that x bar, the centroid position in such case, will be equal to a1 x1 plus a2 x2 upon a1 plus a2, and similarly y bar will be equal to a1 y1 plus a2 y2 divided by a1 plus a2, because we have divided into two rectangles. So area of rectangle 1 is a1 and area of rectangle 2 is a2. These are the two areas which we will be considering. Now what is x1 x2? X1 is the distance of centroid of a1 itself. So centroid of a1 is somewhere here. You can see this is the centroid of a1, which is here at this position, and centroid of a2 is somewhere at the height 4 centimeter from here. Okay, so we can say that at this position we have the centroid of A2. So these are the positions of each of these individual areas. So we can say that the x1 value can be taken as, this is your x1 value. Similarly, x2 value will be taken as this one. This is x2 value, right? The distance of distance of centroid of area A2 from this vertical reference line. Similarly, the values of y1 and y2 are the positions of their centroids individually. So we can say that, and with reference to this reference line, because all the vertical distances will be measured with reference to AB. So for here, this will be your y2 and your y1 will be half of this, which comes here. So you can say it will be 8 plus 0.5, and that will be your 8.5, that distance, which will be your y1, right? And y2 will be 4. So now we have found the values of these numbers. A1 is just the area, which you can easily calculate 8 into 1, and here also A2 is 8 into 1. Now we put the values here and calculate the positions of these centroids. So okay, x bar is, area A1 is 8 into 1 multiplied by x1, which is half of 8, that is 4. Half of 8 is 4, plus A2 x2. A2 x2 same, 8 into 1 area, and x2 is this distance, which you can see clearly that it is equal to 4 also. And then this whole thing divided by A1 plus A2. So A1 is 8, A2 is also 8. 8 into 1 plus 8 into 1. So this way we can calculate this value of this x bar, which is coming out to be, this cancels and we get 4 centimeter, right? And this is very obvious. You can see from this figure that this is located at 4 centimeter from the reference line AC. Now next step is to calculate the value of y bar. In the similar way, we substitute the values of A1, Y1, A2, Y2, etc. So A1 is again the same thing, 8 into 1 area multiplied by Y1. The value of Y1 we can see from here, from the centroid of this area A1 up to the baseline AB, and that distance is 8.5. We put here the value 8.5 plus A2 Y2. A2 is same again, 8 into 1 multiplied by Y2. Now Y2 is the position of centroid of area A2. Of course it will be half of 8, which is equal to 4 from the base AB, and this whole thing divided by A1 plus A2, 8 into 1. And when we simplify this value, 8 into 1, 8 into 1, we cancel and we get this value as here 68 plus 32 divided by 16. So y bar is equal to 6.25 centimeter after calculation. That means the value of y bar, which is the centroid of the whole section, right? This value, which we can see here, this one, this value, y bar, this value is your y bar. So now we have located the centroid of our section, x bar and y bar for the whole section. Now what we have to do here, we have to calculate its moment of inertia about x-axis and y-axis. We know that these are rectangles, and the formula for rectangular section you also know, but that formula, which is BD cube by 12, is about the centroidal axis of that section. So I will show here. If we have this section here, a rectangle, okay, with the base B and the height D, then the formula is BD cube by 12 about the horizontal x-axis, and if this is your y-axis, so we know that Ixx is equal to BD cube by 12, and moment of inertia about y-axis is dB cube by 12. Here you can notice that the cube is for that side perpendicular to the axis. In this case, about x-axis, the depth is perpendicular to x-axis, so we have made the cube of d. When we are taking the moment of inertia about y-axis, we made the cube of b, which is perpendicular to this. So this is for individual, or you can say a single rectangle. You can easily calculate the moment of inertia about x-axis and y-axis. But here we have to calculate the moment of inertia about the x-axis of the whole section and y-axis of this whole t section. So you can see that if we look at this x-axis, which is away from the centroidal axis of area A1, it is not coinciding with its x-axis. So what we have to do that, but these two axes, the own axis of this area A1 and for the T section, these are at some distance, but these are parallel. So we can say that these are at a distance which is 8.5 minus 6.25. So y bar we have calculated as 6.25. So we can calculate the distance between the centroid of A1 and the centroid of the section. Okay. So now what we do, that we find that these two axes, the x-axis of this area A1 and the x-axis of T section, these are parallel. So for that we have parallel axis theorem, which is very helpful in calculating the moment of inertia of such cases, when we know the moment of inertia about one centroidal axis of an area, and then we have to calculate moment of inertia about an axis which is parallel to that. So in that case we have this calculation of this parallel axis theorem, and it says that moment of inertia in our case Ixx will be equal to I about its centroidal axis plus ah square, where I moment of inertia of the centroidal axis of that rectangle about its own axis plus ah square, where a is the area of the section and h is the distance between these two parallel axes. Now we look for our cases here. For A1, if we see, the distance is 8.5 minus 6.25 and the area is A1, and for its own centroidal axis, the moment of inertia of A1 is BD cube by 12. So we will transform it about our axis of the T section. So we can calculate here that this will be BD cube by 12 of this rectangle A1. So B is equal to 8 into 1 cube by 12. This is BD cube by 12 plus ah square. So a is 8 into 1. Now h square means the distance between these two parallel axes. So here the centroid of A1 is at 8.5 and the centroid of the whole T section is at a distance of 6.25. So we take this difference and it is equal to here 8.5 minus 6.25 6.25 whole square. So this is moment of inertia of that rectangular area A1. We also have one more area which is vertical. This is area A2 and it is also 8 into 1. So we have to look for its moment of inertia about x-axis of T section. Right? So in this case we have to find again its axis is not coinciding with the x-axis of the T section, and there is a difference of how much? 6.25 minus, okay, so this is the distance, 6.25 minus 4. So now we calculate here for the second rectangle which is vertical. So for this we have here plus 1 into 8 cube by 12, because here you can see, as we see here, so its height 8 centimeter is parallel to the x-axis, so we will make the cube of 8. 1 into 8 cube is the moment of inertia about x-axis of its own centroid. And then we have area 8 into 1 multiplied by the distance between the centroid of this area A2 and the centroid of the whole section, and that is 6.25 minus 4. 6.25 minus 4 whole square. And when we simplify this sum, we get these values as 0.667 plus 40.5 plus 42.667 plus 40.5, and this total is equal to 124.334. Now what will be the unit? The unit for area moment of inertia is having power 4 of that dimension which you have taken, centimeter or meter, whatever you are using. Here we are using centimeter, so it will be centimeter to the power 4. So this way we have calculated the moment of inertia of the T section about its x-axis which is passing through its centroid. Now we come to the moment of inertia about y-axis of T section. Okay, we write here I, y, y. Moment of inertia about y-axis of this T section. Now you can see here the y-axis of the T section and the y-axis of these individual areas are coinciding. There is no difference between the y-axis of the T section and the y-axis of these rectangular areas. So in that case you can easily calculate by the same formula, just by using that formula, which is either bd cube by 12 or db cube by 12, keeping in mind that the cube will be for that side which is perpendicular to the axis, and then formula will be the same. So Iyy is equal to, for the area number 1, here if we see that this area bd cube by 12, if we apply, so b will be 1 and d will be 8. So 1 into 8 cube by 12, 1 into 8 cube by 12. Then other one is your second area. Now in that case our y-axis is this one, so the base will be 8 and the height will be 1. So 8 into 1 cube by 12. 8 into 1 cube by 12. So this way we have easily calculated the value of Iyy, which can be, when we simplify, it is 42.667 plus 0.667, and this is equal to 43.33. and units centimeter power 4. So now you have seen that we have calculated the moment of inertia, which is known as area moment of inertia or second moment of area for T section. We will be solving some other questions of such cases, but first thing is to be kept in mind that first we have to locate the centroid of the section by using this formula. X bar is equal to a1 x1 plus a2 x2 divided by a1 a2 plus. Similarly, if there are 3 areas, you can add the same thing. If there are 4 areas, you can say a1 x1 plus a2 x2 plus a3 x3 plus a4 x4 divided by a1 plus a2 plus a3 plus a4, like this. Okay, so I hope this calculation has helped you in learning how to calculate the moment of inertia of these plane sections. And if you like this video lecture, please share it with your friends so that they can also get the benefit. And please subscribe to our channel, which is absolutely free, so that in future when we are uploading these new lectures, you will get the notification. Thank you very much.